Um, yeah, I just had one more announcement, which is this is the first announcement of an art show. Um, Here's one example of something that will be in the art show that I thought might work for today. Actually, I'm not even sure this will be in the art show, but in any case, there's a show of the mathematical artwork of Roger Antonsen, who, as many of you know, passed away last year. And MSRI has agreed to host in its space an exhibit of his work. Sorry, SL Math, the Simons Law for Math Institute, formerly known as MSRI. And this is the first announcement for that. So here's a poster. The exhibit will be up from late March to August sometime. We're not exactly sure the start and end dates precisely, but there's a reception on May 1st. And you can register for that at the QR code. I'm going to put this so as not to distract anyone from what we're doing here and from Frank's talk and whatnot. I'm about to post this on the Discord at the end of the seminar. So this will be the first announcement. It'll show up on the Discord in the events tab when the seminar is done. So I just want to make that announcement. And now pass it back to Gabriel to move on to our speaker.
Great. Thanks, Aaron. Well, so our final talk for today, I'm really thrilled to welcome Frank Farris, who is a professor of mathematics at Santa Clara University. He's well known as being a pioneer and advocate for the discipline of mathematical art. He wrote the book, Creating Symmetry, The Artful Mathematics of Wallpaper Patterns. I had the pleasure of meeting Frank a couple years ago at the Illustrating Math Semester program at ICERM. And since then, I've worked with him to organize the art show at the MAA Golden section, and I've really enjoyed sort of hearing about his work and chatting with him, and I'm really excited to hear from him today. So take it away, Frank.
Thanks so much, Gabriel. Thanks to Aaron. I really appreciate the work that you do to organize this seminar. I'm experiencing a lot of forward in my mind are the thoughts of everything that's wrong with the world. So how can I come and participate in a seminar like this one? And I think that's exactly the point, is that staying connected to communities that nurture us is really, I think, the best strategy in this day and age. So already this morning, we've seen a couple people hold up something and say, look at how beautiful this is. And for me, that feeds me. So I hope to ring that bell in you and give you something that you find beautiful for today, because I think that keeps us all connected and gives us a way to move forward in difficult times. So my title is Curves Whose Tangents Trace Tilings. That's a tongue teaser. And I was inspired to do some of this by a student, William Wren, who is here today. So shout out to Will. So, detail here, there we go. So here's an outline of what I want to say. The path to this geometric idea leads through relativity. So I'm going to, for those who aren't familiar with special relativity, I want to give a brief introduction in 2 dimensions. And then we're going to move on to curves in a 2-dimensional and 3-dimensional space-time. And then we're going to talk about some geodesics on a surface in space-time, the straightest possible paths on a certain particular surface. And then we're going to put those together into curves whose tangents trace tilings. So I have a distinctive approach to relativity, which is very much for mathematicians. It's to don't think about the physics, think about the mathematics, because there is a mathematical object that can lead you to better understanding of what the deal is with special relativity and why it sounds so weird, but is really just a nice mathematical object. So we review that Euclidean geometry, everything you need to do in Euclidean geometry, you could think of it as the product, as the properties of a dot product, and how the isometries of Euclidean geometry are exactly those transformations that preserved that dot product, and then, a little more complicated than that. But that's an approach to Euclidean geometry. Well, all I want to do is say that the theory of special relativity uses a different distinctive dot product. So let's just start with labeling some points. That here I have coordinates x and t, one spatial dimension, one time dimension. This represents a point in space-time. And time is measured in years and space is measured in light years. So here is light leaving the origin and arriving at the point 1 light year away after 1 year of time. And so this might represent me staying home, starting at the origin where I am, not moving and letting 1 year pass. And so I see the light arrive over there, a light year away. I'm not sure how I do that, but the light does arrive over there. And I've said, oh yes, the light is going at a speed of 1. So here is the wrong way to measure. So first we're going to analyze a mistake. And the thing that you shouldn't do is to say, okay, this traveler starts where I was, but is moving to this point. And if you think about that, that's moving at about 70% of the speed of light, because we went 1 light year, but it took us 1.4 years. So that's about 70% of the speed of light. So you might think that they see the light arrive at this point over here that's about 0.4 light years away from where they are, and it's √2 time later, and they say, well, it's about it's down here. That's about √2 minus 1/2. That's about 30% of the speed of light. So that light went 0.3 light years per year. Well, that's wrong. That's not how we measure. The speed of light is supposed to be universal. So there must be something wrong in my assumptions about this diagram. So here's the dot product. The facts are encoded in this diagram, which is just like the regular dot product, only with a funny minus sign in what will turn out to be the last coordinate. It looks like the second coordinate here. It will universally be in the last coordinate. So this vector that represents the displacement of me staying home for a year has square length -1. That is a time-like vector. It's pointing into time, and that's how I travel. I go ahead in time. This vector has square length 1. That is a space-like vector. It represents an impossible jump 1 light year to the right. So here are 2 time-like vectors with the same square length. So this is weird. It looks to us like the vector 1√2 should be longer, but no, it also has square length -1. So that somehow has to be the same as the vector representing me staying home. So it should be indistinguishable by physics. That's the lesson of this dot product, that when the things look the same to this dot product, they really are the same. So each of these, because the vector there has square length -1, that means that they experience 1 unit of time. So if each has a calibrated clock, this traveler whizzing away at 70% of the speed of light, their clock is going to tick once if it ticks once every light year. The second thing that's weird is that the traveler must have a different view of what's simultaneous. I'm going to have to frame space-time with a pair of orthogonal vectors, one time-like, one space-like. So for this person who traveled, they see the point that is 1 light year away from where they started as being this vector. The two are perpendicular to one another, and they frame space-time, and the light that they saw leave there has to arrive over here in order that they measure it to be the same time. So it's weird that the length of light-like vectors is 0, but we learned to live with that. In fact, these two frames have to be considered the same. The traveler, being going at a uniform speed, can't really tell that they're whizzing by me at 70% of the speed of light. I can see that, they can't. So they think that I am moving left because these two frames for space-time have to be the same. You can transform between the 2 points of view with this matrix. So that matrix is a typical isometry of space-time. So every pair that has 1 unit time-like vector and an orthogonal unit space-like vector, all of those frames, if they're perpendicular to each other, should be indistinguishable by physics. And you can transform between the points of view with this matrix. Nice use of the hyperbolic functions and nice analog, continuing the analogy between hyperbolic trigonometry and regular trigonometry. So let's start thinking about curves in space-time. I've got a couple of them drawn here, and the top curve going along this upper hyperbola here, that's the set of time-like vectors. You can't travel along there, so I don't want to think of that first. I want to think of this one. I could travel along that one because the tangent vector to this one is a time-like vector. This could represent the experience of a physical being. And this is an example that parameterizes the hyperbola. I'm going to use the parameter u. And you think, what is u? Well, it turns out that u is proper time. It's the correct way to parameterize this curve. This person thinks that they are traveling at unit speed calibrated to their standard clock. And let's just look at the tangent vector to this curve. You can verify that that tangent vector is a unit, it has square length -1, and therefore is a unit time-like vector. And the acceleration is actually proportional to the position, which makes it awfully like a circle. And that 1 there is going to be the curvature invariant of this kind of curve. So this is the analog of a circle in Newtonian physics. It represents someone who started far away from me, is accelerating toward me, and then accelerates back away. It's the best you can do, according to special relativity, to have constant acceleration. Because after all, if you accelerate constantly, literally, you would soon exceed the speed of light. So all that can happen in special relativity is that you can start looking from my static point of view, like you're getting faster and faster and faster, but you have to be asymptotically approaching the speed of light. So that's a pretty weird thing to get your mind around. And yet the analogy to the circle is pretty comfortable. It's just the analog of a circle in this different geometry. You can have general curves. You can make one, call that unit tangent vector t, and you could name it by a parameter theta, and you can make the theory of this is very a mathematical development that's highly analogous to the theory of curvature in the plane, that theta, the curvature of this curve, is the rate of change of that angle. So I'm going to go quickly here because the mathematical details might not be so important, but you can develop a Tn frame for this curve, and the curvature is a relativistic acceleration. So here are curves with curvature 2, 1, and 1/2. So for more general curves, you can recover the curve from the curvature function. This is probably not very relevant, but I said, what would it be like to have a curve whose curvature was the cosine of the time I was going at? And you could make it be parameterized correctly and integrate back. And you get this blue curve here. If you choose sine instead, you get this one. But you could have just, instead of choosing sine, you could have just started half a period or a quarter of a period earlier. And these paths really are congruent by a transformation of space-time. So that's another weirdness. So in up a dimension, I just want to say that curves have both a curvature and a torsion. And the torsion is the thing that measures how much the curve fails to be in a two-dimensional space-time. Just as in the theory of curves in 3-dimension, the torsion is the measure of the failure of a curve to lie in a plane. We'll use that later. Okay, so let's go with 2 space dimensions and 1 time. The set of unit time-like vectors is -1, and that looks like this, using how GeoGebra makes it look. So this is an object that is interesting to study in its own right. These are all the places you could arrive from here now by going on 1 unit of time and traveling less than the speed of light. So, and I want to give a shout out to William Wren, who came to me and said, we had parameterized this another way. I'd used the rotationally symmetric parameterization, and was studying this a little bit in our differential geometry class. And he said, doesn't this parameterize it too? And at first I said, no, I'm sure that's wrong. And then, wow, that's a very interesting parameterization. And it turns out that it bore a lot of fruit and led me to these curves whose tangents trace tilings. So certain geodesics on that surface are easy to identify because you could just slice it with a plane. If the V curve, if you set the parameter V equal to a constant, then this curve lies in this plane. And there's the formula for the plane. You can see that it does. And then the formulas work out to show that that curve has no acceleration along the direction of the curve. It lies in a plane. So these are just like the meridians on a sphere, where you slice the sphere with a plane through its center. So, if you're teaching differential geometry, you say, wow, look at these geodesics, they're so cool. But then a student might say, well, what good are those? More on that in a minute. I want to point out a beautiful stereographic projection. Just like on the sphere, you can project the meridians of the sphere to be circles in the plane using conventional stereographic projection. Here, you project from the point down here, -1. That is the other pole of this hyperboloid of 2 sheets. And you just project down there. The intersections with a plane here turn into those beautiful circles that meet the boundary at right angles. That is the Poincare disk model of the, you project there, of the hyperbolic geometry. The geodesics project to the hyperbolic lines in the Poincare disk. So the geometer in me said, look at these geodesics, they're so cool, they're the hyperbolic lines. And William sort of said, well, who cares about these geodesics? Because after all, these are not paths that anyone can travel. It's not, their tangent vectors are spaceline. Like, you can't move in space-time and go along those curves. So why would these be interesting? And so then I had the insight that, these geodesics, they're sets of tangent vectors. Those explain what's happening to a traveler as they go along a legitimate path and their tangent vector is changing. That's what they are. The paths have constant relativistic unit curvature. And in fact, they have 0 relativistic torsion because they lie in a plane. So these are just those hyperbolas that we showed earlier with curvature 1, but they're in different planes. Okay. So that's a thing that what these geodesics do is they're a collection of tangent vectors. They're a parametrized collection of tangent vectors, parametrized in the right way to explain this motion that can be realized, a motion with constant acceleration, or as constant as you can have in special relativity. So their tangents trace geodesics. Yeah. So these are the curves whose tangents trace geodesics, these hyperbolas. So then, it's too long a story. I had this idea on an airplane going to Europe that, their tangents trace tilings. And I was away from mathematical software for 3 whole weeks. So I was sitting on my vacation going, oh, these curves, they've got to, how do they go like this? So anyway, it was very joyful for me 3 weeks later to get back to my software and say, oh yeah, this is what they look like. So here's a typical tiling of the hyperbolic plane. These triangles, in the sense of the metric that is inherited on that hyperboloid of 1 sheet from the relativistic metric, those triangles are all congruent. They're all the same size. They're all, just the same angles. So what path with unit time-like tangent vector traces the central triangle in this tiling? So it's going to, start going that way, and then it's going to move to go that way, and then it's going to move to go this way and this. So that tangent vector is continuous. So I'm going to recover this path by integration, and I'm just going to start my path at the origin where I am. And it would consist of 3 pieces of hyperbolas, each in a different direction. And those hyperbolas are going to join in a way that makes them tangent. They are once continuously differentiable, but not twice continuously differentiable. Yeah, so that's what that says. Continuous with a continuous tangent vector, but discontinuous acceleration. So now, for the meat of things, what would it look like? So I sort of had a picture in my mind, and then it was really fun to make that happen. This is what one looks like. So, and that single point of view is not so great. And I admit to being like foolishly delighted by the shadow cast there. If we're in space-time, that's the other sun that somehow puts light on space-time. No, so anyway, it's just to help you see, because when you look at an object and you can see its shadow, that gives you a little more information about what the object is. So each piece is in a different plane. This is a different view. You might be able to see the planes that those pieces lie in. And then you see, if you look straight down on it, then it looks like this. So it delighted me to be able to see this. I want to tell you a little bit more about these things. And here's the first thing, is that with that triangle, you might consider starting at each of 3 vertices. So that'd be 3 different tangent vectors for your curve, and then they wind around like this. These are three congruent paths. They meet at the top because on the average, that tangent vector going around that triangle is a vertical vector. So it's, that you should arrive at the other end where that little gold bead is. And those paths all arrive at the point 005.4. That's, I'd have to write formulas for this, but that's the time it takes. Or that's, if I were sitting there waiting for those people to come back again, it would be 5.4 years later. And yet the traveler spends about 4.6 years making the trip. The parameter time is 4.6 years to go around those things. And this is called the twin paradox. So it delighted me that this, sort of goofy idea about making curves whose tangents trace tilings also gives you a quick way to just live with the reality that when someone is out accelerating in the universe, then time passes differently for them than for me. And that I can sit here for 5.4 years waiting them to come back. And they'll say, good to see you. It was only 4.6 years ago that I left. So it's a delightful, weird thing. And again, I can't say too many times how much I love that goofy shadow shining with what? It's a different kind of light. So if you travel the other triangles in the tiling, then here are 6 of the nearest congruent triples of trips. Here's the tiling. Here are the curves whose tangents trace tilings. And looks like I forgot to put my little gold beads on the top of those. I like the gold beads just because they're pretty. Yeah. Why not? Then there are other tilings. There are just, there's infinitely many tilings, so there's a lot still to do. So here's one with squares that meet 5 at a vertex. So this is how the square looks. It's got 4 of these graceful things that twist around. And again, I'll come back to the beginning, and that's because the tangent vector is going around this square, and on the average, the tangent vector is vertical, meaning that it's just, they're all 4 going to end up in the same place. Here's a view of many congruent trips with a sort of semi-transparent reflecting light shade instead of the hyperbolic surface there. So that makes it look sort of imponderable and, mysterious, weird. So these are curves whose tangents trace tilings. So I can say just a little bit about how these were created in Rhino with Grasshopper. I think Dave Bachman is here, and he taught me Rhino, and I'm so grateful. Henry helped me learn Rhino too. This is what a Rhino window looks like. You can see multiple views. You can see a rendered view. You can see a wireframe view. But how do you create those curves? Rhino is a British software designed for architects. And I'm aware I'm hearing beeps on Discord and I can't see it because I'm looking at only one screen. Rats, a single screen. You can get a free 90-day trial if you want to try it. But the thing that makes it powerful for mathematicians is a plugin to Rhino called Grasshopper, where you can do plug and play programming. And so this is a screenshot of my awful code that makes the first hyperbola, the second hyperbola, and the third hyperbola, realizing that you can just get the 3 of them by rotating a certain way, and then you move them around, and they're created by NURBS in this green component there. You give it a list of points and it'll make a beautiful curve there. Later you can put a pipe around it. So I think this is really important for our community because the approach through Rhino is really a mathematical approach to the CAD process. In many other CAD processes, they assume that the things you want to make are, like things that are already known, whereas this allows us to make things that maybe nobody has made before, maybe nobody has tried to see this before. So I highly recommend this, and I'm just boundlessly grateful to the illustrating mathematics community for getting me involved with this and being patient with my learning as an older person. This was my second Python box that I made. I'm learning still. Okay, so and another thing that charms me about the Rhino Grasshopper interface is that you've got this sort of virtual thing in your Grasshopper window, and then you press a button that says bake, and then it becomes real, meaning that it gets turned into a mesh in the CAD program. I love that. So this is my artwork from the joint math meetings last year, and it is let's look at the right here. This is a tiling with those squares that meet 5 at a vertex. And I've colored the hyperboloid there with a wood grain that's made using Peter Stampfle's online hyperbolic kaleidoscope, and then sort of put onto that hyperboloid. And then I've got my wireframe things here with the little gold beads there. And I made the one at the center gold with some kind of explanation of starting here and going along those 4 paths, and then all these other paths. So that's what the right-hand thing is. What are those on the left? Well, that's my last little bit of my talk here, is to explain these. These are curves whose tangents trace tilings on the sphere. And these two ideas kind of came together for me. So when I was on my vacation, I was also looking at these piecewise circular curves. So let's build up to this one a little more slowly. If you divide the octahedron into 8 triangles, divide the sphere into 8 triangles, you'll get an octahedron exploded out onto the sphere. And then you think of those as tangent vectors of trips. So you go along one of those curves, and you'll have a curve whose tangent is a piece of a great circle. And that curve, when you integrate, is itself a circle. So you recover the curve by integration. And each of these blue curves is made of 3 circles. So trace each triangle 3 ways, and you'll get these 3 things that meet at a vertex here. Again, the average velocity of these curves, or the average tangent of these curves, is just a ray that goes out from the center and meets one of these beads. It's interesting that they intersect. Time is short, and I won't say more about that. Here's tracing the cube projected to the sphere. You divide the sphere into 6 squares, which can be done. And then you get these by 4s. These are emerging from a center. They all start there. Their tangents trace the tiling in these different ways. You can do this for any polyhedron. And here's the dodecahedron with the tangents at the same time. And this looked completely awful when I had only the curves there, because it's just this spaghetti monster at the center. And so I put that ball there to give our eyes a little relief from the awfulness of, oh my God, there's so much going on in there. But you can see those pieces emerging from that center, and you might be able to imagine that as a tangent vector goes along the pentagon in the dodecahedron, then these curves, these 5 curves, are the ones that trace that dodecahedron and all meet at a point with the same average velocity. Yeah, that those visual intersections, when I saw that, you know, I was loving this work and thought, that's awful. We don't want that. So here is just the idea that I was consistently only using one orientation on these triangles or squares, but I'm going to trace the cube faces, those squares, and then I'm going to trace them backwards in order to get 8 curves that meet at these little gold balls out here. And then if you start at any point, then you trace out a surface like this. And these surfaces really sort of mystify me. I have not, I really tried for a while to explain them to myself in a way that made sense, where I felt that I thoroughly understood them. And then I saw a dog with a fluffy tail and got distracted and went and did something else. So this is something to come back to, is to understand these surfaces. They really do have flat pieces on them. So yeah, they really do have these 3 petals on them where vertices meet that are actually pieces of a plane. So they're very intriguing. And, you know, I'm a sucker for ray tracing, and, you know, put a little wood grain on, make it shiny, and that's my idea of a good time. So, and then the last thing that I want to show is these Archimedean solids. These are, which one is this? This is a truncated octahedron. It's got 8 hexagons and 6 squares. So for the hexagons, you can see 6 coming around here. For the squares, you can see 4 coming around here. And here's one where the shadow really is intriguing and complex. So, and that's really all I had to say. I was so conscious of time, I sort of rushed things. But there are all these Archimedean solids. There are still, you know, more polyhedra to trace. And so I have I think this is a rich project that's going to keep me busy for a long time. I have not, I've got like a draft of a paper in progress, but clearly this is going to take some time to write up carefully. So that's what I have to say. I finished early. How about some questions?
Thank you, Frank. I'm wondering, yeah, does anyone have any questions that they'd like to ask while we've got this Zoom chat open?
And I'll leave the share on in case somebody wants to go back and see a slide. But otherwise, I'll close it.
Is there a so you have tilings of hyperbolic space and tilings of the sphere. Um, is there any sense of tilings of the ordinary Euclidean plane that you can do this
Yeah,
trick
I
to?
spent time thinking about that and convinced myself that you can't do that. Or I can't, and I can't explain why not. But I did certainly think of that because it would be rich. But you're like in the sphere, there's the origin, and the sphere is a reference point where you could have the tangent vector going from there to there. In the plane, once you set up a reference point, then those triangles in the tiling are not treated reciprocally. You know, there's maybe the triangle that contains the origin, and then the triangle next door will be completely different. There's nothing symmetric that I could think of to do. But it certainly is a natural impulse for, last year I taught the 3 geometries course again, that you can do something for the sphere, for hyperbolic plane, you got to do it for the plane too, and I couldn't think of anything. So
Yeah. Maybe it just doesn't work, yeah.
yeah.
Well, I mean, this maybe leads into the question I had. It sounds like here you're treating the hyperbolic plane as like a space of velocities,
Yeah.
sort of relativistic velocities. And so the plane, of course, is the space of Galilean velocities. So it seems like you could presumably do the same thing. And the doubt there is that I'm not sure I understand exactly what you're doing in the relativistic case, or the special relativity case. So I'm not sure what the same thing would mean in the Galilean case.
Well,
So could you
it's pretty
say?
concrete. In the hyperbolic plane, you have these tangent vectors. The possible ways you could go from here, the ways you could head from here, is that hyperboloid. And so I'm moving along there in a way that creates a curve that goes like that. Except I'm going to move that curve to start at the origin. And then I'm going to start at where I was before. And then I'm going to start where I arrived. And that's how you make that blue circuit that we saw coming up and around here. So
So
in
it
the
sounds like
plane, if you start somewhere and go along a triangle and then go along a different triangle, then you're not, I mean, maybe if you move up in space or something, I can't, it's like it destroys the symmetry of the tiling, which for me is kind of the point.
so so it sounds like you're identifying all of the forward hyperboloids in the different light cones by like translation of spacetime.
Yeah, and
I see, okay.
it's common practice in physics to say, I've got this velocity vector and it's really representing a particle out here, but I'm going to use a formula for that makes it a vector at the origin. So in space-time, I've got these things that are vectors out there, but a vector is a quantity with magnitude and direction, not a vector with a starting point and a magnitude and direction. So I'm bringing all those tangent vectors to a common reference point. If you do that for conventional curves in space, like those circular things, I'm taking all those different tangent vectors and saying, oh, those are just points on the sphere. So that's what makes this fly.
That's
Other
interesting. Thank you.
questions?
I
Go
have
ahead,
a
Dave.
question, Frank.
Yeah, go ahead.
Each piece, it looks like it's the same at each end, right? If you turn like one of those green leaves 180 degrees, it would fit
That's
back
correct.
in. So
Yeah.
you could treat one of the corners as a new origin and kind of repeat that picture, and it
Yeah.
would still fill up the 4 pi space at each point. I wonder what that tiling would look like in 3D, and whether there'd be a lot of self-intersection, or
Yeah,
whether it really
they'll
work.
typically be heavy self-intersection. I don't know if there's a way to start with sort of a minimal example where that would look nice. But I thought of that. I mean, the way you can see the other side is like here for this back white bead there, then its negative is there. And so what you're saying is you could put another copy of that up there and keep going out and then put in the rest. Yeah. It might be delightful that, you know, if those would like join the ones at other points, but maybe they'll just interfere and look like my dodecahedron with that big spaghetti monster at the middle. Who knows?
Frank, that was very nice. Thanks.
Thanks.
This isn't a very well-formed question, but is there some sort of anti-relativistic space-time explanation of the paths on the sphere? Obviously, it wouldn't have anything to do with real physics, but is there some explication of the twin paradox where the moving twin is older or something?
Yeah, except it's just as boring as the line is the shortest distance between 2 points. So in this case, when you go directly, like maybe I can trace it with my mouse, when you go directly in a line from the center of the sphere to there, you're going less distance than these curvy things. So to put it another way, the twin paradox is the opposite of that, where a straight line takes longer.
Right. Okay. Yeah, I see.
Yeah, isn't that
Thanks.
interesting? You've given me a sort of an image to maybe use in the eventual explication, you know, expository article about this.
Yeah, sure. Thank you.
Yeah, thanks.
Frank, I think I have a question.
Yeah, good, Reese.
I think I might have missed something a little earlier in the presentation, but why do we not want any of the paths to intersect with each other?
It's not a matter of want, it's that sometimes they do. So like this is the first example where it's just not going to go. Anyway, this one has self-intersections too. It's that I probably can't explain this on the fly, but you see there's an intersection over there. That's like going around this way is the same as going around this way, and you're just going to meet. So I think it's a little more, I think the picture without the mirror image of this is prettier than the one with the intersection. So this is the one with the intersections all over the place.
If you're going to make it physically, you want those intersections.
Yeah,
because
that's a
they
good
increase
point.
the structural stability of your,
Yes,
of your
yes.
object.
So if I was going to 3D print one, I probably would print this one. Yeah. And I just haven't been encouraged to do 3D printing recently. So I haven't tried.
Okay, so if you don't mind me asking, what does the intersections mean? Does that just mean that
It means that
along
there's
the same
two
paths?
ways.
Oh.
There are two paths with different velocities traced out that end up coming to the same place.
Okay, perfect. Thank you.
And it's probably like if you're doing the edge of a square, if you started at opposite edges and went this way, then probably those paths would cross. Yeah, what interesting questions. Anybody else? What you got? I think I'll stop my screen sharing. Well, I hope you agree that this was worth spending time with. It's you know, it's delighted me. For me, this is the most beautiful thing I've found in a while. So. And I guess I also wanted to say, you know, with everybody talking about AI, you know, our community has humans that notice things and say, look, this is beautiful. And I don't see that function of humans being replaced by AI. So I'm grateful to be part of it. So I interrupted. Someone had a question. Sabetta, yeah.
Hey, I just, maybe this is a question you addressed and I just missed because I was staring at pretty pictures and not processing all the words. But is there a sense in which there are like boosts or like isometries of like Minkowski space that are representing like taking like one of those like lobes into another one, or it's
So
that
the
way?
one that looked like you know, a little sort of flower, a little twist coming up to here. In the same picture, there were others that looked like that. Those had been transformed into that other one. So that was a bunch of paths that were all congruent to one another. And you
Okay.
look at them in the model, and it looks like, and this was on the poster for the talk, that there's this beautiful regular thing there, and then these squished things off there. And though that's, you know, part of the gestalt of space-time is to say, you know, you're forced to admit that all those are identical. Yeah, thank you. Yeah.
Thanks.
Yeah, if you have time for another one. So I'm still a little confused about why you say there's a loss of symmetry somehow, or that it's fundamentally different for a plane. And the reason is that it seems like you could draw these paths. Like it's true that if you want a tiling, these polygons have to be a certain size. But it seems like if you just want to do a single square, for example, or a single triangle,
you can do a single square, sure.
yeah, you could make
Yeah.
that hyperbolic polygon as small as you want. And as it gets smaller and smaller, it goes to the Galilean limit where that hyperboloid becomes essentially a plane. You're in the flat part at the bottom, and the symmetry group approaches the Galilean symmetry group. So if there is, you know, it seems like if it works for, you know, in the relativistic case and the hyperbolic case, it must also work in the Galilean case, because the
I just
Galilean
think
case
that
is a
the
limit.
limit you get, I don't understand the limit concept there, but it seems to me that curves will degenerate to single points. But yeah, if you want to, if you've
Yeah,
got a way of making the curves in the plane whose tangents trace a tiling in the plane, then I'd love to see that.
yeah, I mean, you literally do what you are doing with an
Yeah.
extremely small polygon. You don't have to make any changes to your setup. You just have to make the square very, very small.
It's just, it seems to sort of, the square next door is going to be treated differently if you agree to start all your paths at the same place. Maybe that could be a key, is don't start all your paths at the same place.
Well, but again, it's not different. It's if you consider those two squares to be treated the same in what you're doing, then you should also treat them to be the same. You should also consider them to be the same in the Galilean case, because it's the same symmetry group. Like,
Well, I think the challenge then, and there's somebody in the chat agreeing with you, send me the pictures. I want to see it.
Okay.
That's the
Yeah.
test of the idea is, you know, send me the pictures that show what you mean. Because it's, you know, it is hard to understand in words, and that's kind of part of the point of our wonderful community. So,
yeah, maybe, yeah, I agree with what's being posted in the chat. So
yeah. Okay, and there's more on Discord. I will be able to see Discord later. So I'm supposed to start office hours at 10, but I'm going to stay until somebody knocks on that door. But it probably means that I don't interact with the Discord very much. But my goodness, it's wonderful to see these names on the screen. Not seeing everybody wave hello. Hello. Oh, Helen, good to see you. Carlo. Yeah.
Well, we have reached the top of the hour, so office hours are starting, and maybe we should wrap up. Let's see, Gabriel, did you have anything you wanted to say before we close out?
I was just going to thank Frank for a wonderful talk and for giving us so much to think about, and to just sort of echo that the Discord seems to be engaged with this idea and this challenge. So I'm really excited to see sort of how this continues. But that's really all I had to say. Yeah, thanks so much. It's great to see you, Frank, and that was a lovely talk.
And you were going to post the thing for Roger again?
I will post the announcement in the events channel on the Discord, the events tab on the Discord channel, shortly. So yeah, thanks to Frank for a lovely talk. Thanks to Henry and Dave as well for your presentations. Very nice. Extra thanks actually to Frank for, by the way, for always being here in the background to help out with Zoom technicalities when we have issues. You're always there to solve them. So thank you for that. And thank you, the rest of you, for coming. Thank you all for being here. Great to see you all. And we will do this again next month. So we can continue the social hour on the Discord, and I will stop the recording and sign off from the Zoom. Thanks, everybody.
Valentine's Day.
Yeah.
Thanks, everybody. I really appreciated the support.
Thank you, Frank.
See you soon.